So today we are going to look at the weak or so-called variational formulation. And we're going to look at the weak form from different points of view, right? There are a couple of ways that I like how to get to the final weak form, and then to the discrete equations as well. So if you recall what we looked at in nonlinear mechanics, we kind of talked about this abstract idea that we're living in an infinite dimensional space where everything is possible. You can obtain your exact solution no matter what, right? So that is basically the idea. The moment we go to a finite dimensional space, this is the moment we are actually able to solve finally the problem. So in this first lecture, we're going to look at the variational form, which is an alternative expression of equilibrium. We kind of relax the idea that the differential equation has to be satisfied point-wise everywhere along the bar, but on average. And this will lead to a different statement of equilibrium that in a sense is equivalent to the strong form. And I say equivalent because they are both living again in an infinite dimensional space. So one is able to obtain the exact solution just because you have the ability to represent any function, and the same as the other one. So these are equivalent statements in a way. And there are proofs that you can go back and forth between one and the other, right? The moment we discretize the equations, we're no longer living in an infinite dimensional space. So there's going to be an error, most likely. There are simple problems for which you can get the exact solution in the projection. But for the most part, you are going to get an error. So again, the whole point of this course is that if you are able to understand the error, right, and you can control it, then you are okay with having an error. So that is the whole point. So we're going to look at the weak formulation. We're going to state the weak formulation in abstract form. And then we're going to look at a couple of mathematical theorems, right? Just to show you why the Galerkin, the Galerkin projection in a way is so important. And then we're going to look at examples as we do in every class. So, as we said, the strong form, if you recall, we had the differential equation and boundary conditions. This defines what we call the boundary value problem, right? Otherwise, we cannot really, we don't have a proper problem. So the statement has to be the differential equation on the one hand, and on the other hand, the boundary conditions. For the bar, how many boundary conditions we needed? Yeah? Just two. Why do we need only two boundary conditions?
Well, you need if you have a Neumann boundary condition, then you have like an infinite number of solutions. So then you need the Dirichlet condition.
Well, you are pointing to a pure Newman problem, and we're going to talk about it. But you need only two boundary conditions because it's a second-order differential equation, right? So if we try to integrate this, there are going to be two constants that arise after integration, as most of you who took the nonlinear exam, nonlinear mechanics exam, remember. And so those constants are fully determined with the boundary conditions. Okay. So we're going to say something here. We're going to try to say that we don't want the solution to be satisfied point-wise everywhere along the bar, at every point. That may be too restricted a requirement for a problem. So what we're going to do instead is we're going to make a statement of equilibrium on average sets. So what we do is we take our differential equation, right? If you remember, this is the differential equation considering this spring that was trying to constrain our bar laterally, right? And negative because, of course, the force is in the negative direction of the displacement. And then we have our force per unit length, right? We're going to multiply that by a function. We call this function a test function or a weight function. And then we're going to integrate over the entire domain of interest, our entire bar, and we're going to set that equal to 0. And we're going to say that this is going to be the case for every weight function in some space that for the time being, we're gonna call the energy space, right? And we're gonna talk a little bit about that in a minute. But what I just outlined is the so-called method of weighted residuals, okay? So what we do again is we take our differential equation, we multiply by some test or weight function, integrate over the domain, and set that equal to 0. So what we're saying, in a way, is that this weight function and this differential equation are somehow orthogonal, right? And again, this is, I believe, really the cornerstone of what we do today in simulation. We're going to talk a little bit about that later in detail. But what we're saying, think about it. The moment I set this orthogonality condition between my differential equation and my weight function, right? I'm saying that these two things have to be orthogonal, right? But it's not only one weight function. It's a set of weight functions, right? It's a space. We call that the energy space. Okay? So in a way, what we're saying is that our differential equation has to be orthogonal to an entire space of functions, right? And so we're going to keep this in mind, and later we're going to go again in more detail to what it means. We're going to try to understand it, because of course right now this seems to be very abstract. Remember, we're talking about functional spaces in this course, right? These are not our usual Euclidean spaces we're used to, right? Like you see a vector in Euclidean space, yeah, you understand a vector, you know how to project a vector, you know how two vectors are orthogonal to each other. These are concepts that we understand. But when we start dealing with functions, things become more complicated, right? And that's what we're going to understand in this lecture. Okay, so what is this energy space? What we say is that the energy space is comprised of functions for which we can simply get finite strain energy, right? So mathematically, right, this is defined as a set of functions v, yeah, for every x in the domain in omega, such that my strain energy, where I'm going to represent with this u, is just finite, right? And strain energy for this problem can be written in this way. We all know how strain energy is computed for a bar, right? In a way, I said that you can get the variational form in different ways. This is one way to get it, right? There is another way. Most people also are familiar with the minimization of potential energy. So we could actually start from potential energy and then just apply a directional derivative and then obtain something that is going to be looking like this, right? Again, not yet, because I have to work a little bit on this function, on this functional. So that's what it is. Strain energy being finite is what we want, and obviously it makes sense, right? Because we don't want our bar to explode, right? There is really no point in having something that goes to infinite. There is no infinite strain energy. When you reach a value of strain, things simply break. So it doesn't really make sense to have infinite strain energy. So we're going to be working with the so-called energy space. All right. So mathematically, we have these ideas. Now that I'm dealing with spaces, it's a functional space. Remember, it's not a Euclidean space the way we're used to. Now we're dealing with functions. So the moment you're dealing with functions, you start thinking, well, how can I measure things, right? Well, you need some norm to be able to quantify something in a functional space. The same way I can take a vector, right, and then find the norm of a vector to understand how long that vector is, right? I have to be able to do the same with functional spaces. So what mathematicians say is that, okay, the energy space induces the energy norm, and we write it like this, and energy norm is simply the square root of the strain energy. And now I have a means to measure things, right? I'm going to say that essentially the norm of this function v, the norm, I'm just going to compute it as the square root of the strain energy of that function v. Yeah? So again, this is our way to measure functions now that we're dealing with functional spaces. And you can see it, well, this is analogous to the Euclidean space norm, where you just take the norm and you basically take the square root of v dotted v, right? That's the way we normally measure the length of a vector in Euclidean spaces. But now we have something that is going to help us measure things in functional spaces. So this, of course, becomes fundamental when we try to do, for instance, convergence analysis, because when you obtain a solution, well, you want to see how good or bad your solution is. And to be able to understand that, you need to measure and then take the difference with respect to something, right? That something is going to be an exact solution, for instance, right? And so we are going to be able to now measure things in functional spaces. All right, let's work a little bit on the variational statement, because if you see the first equation, what do we notice? What is the differentiability requirement that we place on the function u? 2. So I understand from this equation that u has to be differentiated twice. And so we're going to relax that and want to say, well, I want to balance the derivatives, right? I want to say that this function here has no derivative. The function u, we have to apply the derivative twice. So let's try to balance the derivatives. And so we apply the so-called integration by parts. You guys all know that. And so we can write that term the way you see it here, right? Where now we have a term that is really balancing the derivatives. And then suddenly we have this term, right? This is the boundary term that arises naturally by just simply doing integration by parts. And we looked at this result also in the nonlinear mechanics class. If you remember, it was, to me, it's incredible that in the formulation, the natural boundary conditions just arise naturally by simply doing or manipulating an expression, right? And this is really your boundary tractions. So EA du dx, if you remember, was what we defined as the axial force, right? And then, of course, we have to apply it at 0 and L. And that basically means that those are the values of the axial forces at the ends of the bar, right? Our boundary terms. Okay, so now that we have that, we just simply plug it back into the expression. And then we have now kind of a different statement of equilibrium. Again, we're looking at equilibrium in a weak sense, right? On average along the entire bar. And then we have on the left, we have the expression that is really balancing the derivatives. So now potentially, I will require only a C1 function for you. I don't require anymore a C2 function, right? I just simply need a function that is going to be continuous, right? And first derivative continuous, right? That's all I need. And then I will be able to work out with, for instance, linear polynomials, because I can apply the first derivative and they're going to be continuous. Otherwise, it wouldn't be possible. Okay.
I do have a question.
Yeah.
So are we still allowed to have discontinuities within the integrand? So that, for instance, if you have first, let's say a linear function, and if you integrate it, then you get basically a straight line. But if for some reason there's some sort of discontinuity, the slope changes.
Yeah.
Can we just then split the integrals in two and then solve it still directly?
Yeah. So normally when we deal with discontinuities, things get a little bit more tricky. In a way, you are dealing with a different space of functions, right? Some people, we will talk about the Sobolev spaces later, but Sobolev basically means that you have to have the functions that are square integrable and whose derivatives are square integrable. We're going to look at, in this same lecture, at all of this. But essentially, when you have a discontinuity, then if you have a kink in the solution, like in a weak discontinuity, then there is no, the derivative is not defined, right? And so now people talk about what is called the broken Sobolev space, where indeed you can have square integrability of the function, but then you have to do something special about the domains to the right and to the left of the discontinuity. But this is going really way beyond what we want to discuss now, but we're going to look into that later.
I had a brief question about the orthogonality requirement you stated. That was the requirement on the integrand, right? So the integrand has to be 0.
Yeah.
Integrate over
Yeah. Okay. So now we have a variational statement of equilibrium. And again, remember that this expression here has to hold for every function w in that space. Every function, right? So again, the orthogonality is not between two functions, the differential equation and some function w. It's between the differential equation and a very big set of functions that live in certain functional space, okay? And again, you notice that the boundary term pops up naturally by doing integration by parts. So this is our statement of weak equilibrium for this very simple one-dimensional problem. Of course, the weak formulation, you could obtain it for any problem. And so normally what you find is that people describe the weak form in abstract form, right? And so what we're going to do is we're going to take the left term and we're going to say, well, this is going to be called the bilinear form. Bilinear form because it's a function of two functions u and w. That's the reason it's bilinear. And it's a linear function of those two, right? And then on the right-hand side of the equation, you have the so-called linear form. And you notice that there is no u anymore there. And I say there is no u, although there is a u here. But remember that this term is actually the boundary condition. So this is actually known, right? So this whole term here, we're going to call it the linear form. And the bilinear form, as you can see in this expression, has some properties, right? So if you assume that you have u, v, and w given from some certain space, and then you have a constant c, then the bilinear form has to be greater than or equal to 0 if you apply that to the same function, right? So in a way, you're saying this is bounded below. The bilinear form is, you have a symmetry condition, right? So b of uw is equal to b of v, sorry, uv is equal to b of vu. And so you can notice here, if I look at this bilinear form, I can simply swap u and w and I get the same expression. So it is indeed symmetric. And then you have a distributive property, right? b of u plus v comma w is equal to b of u comma w plus b of v comma w. Yeah, so you have a distributive property. And so the statement of equilibrium, normally people do it like this. The variational form is find u in the energy norm such that the bilinear form is equal to the linear form for all weight functions in that energy space, right? And of course, this is abstract because, again, the forms, the actual forms of the bilinear form and the linear form, you define them later. And they are going to change depending on the problem. If you have a one-dimensional bar in tension or compression, then it has some form. If you are dealing with a heat conduction problem, for instance, it has a different form, and so forth. Okay? Now, if you recall, we did manage to get a way to measure functions, right? Remember that the energy space was inducing a norm. And so if now I can compare, because if you look at this term here, the bilinear form looks incredibly similar to the strain energy, right? So if I replace basically this W by U, right, it's basically 1/2 of that. And this is what this is saying. So there is a relationship between my strain energy, right, and the bilinear form applied to the same function, right? And so if you recall that I can obtain, or I can measure, right, in the energy space, I can measure a function U. Now I have another way to measure that same function. Remember, before we defined that measure with the strain energy. Now I can define that measure using the so-called bilinear form, right? Because there is indeed a relationship between these two. And this is very, very important because eventually, when we get to the discrete equations and to be able to understand or to obtain errors of the finite element solution, right? Now I can compute these guys, right? I can compute it because essentially the bilinear operator is going to translate eventually into my stiffness matrix for the problem. Okay? So I will be able to get that B of U comma U. 1/2 of that, well, that's it. That is basically the measurement of that function in the energy space, right? That is the energy norm. Okay? So keeping these things in mind, what we have done so far is essentially transform the problem into something that guarantees that you have point-wise equilibrium in the bar to a point where we assume that we're going to have, equilibrium on average. And this is not important now because, again, remember that we are still living in an infinite dimensional space. So this statement of equilibrium is equivalent to the strong form. You can go back and forth between the two. And in many finite element books, they do so. They prove this with a theorem, right? But this form of the formulation becomes really the basis from when we go to a finite dimensional space for instance, using finite elements to obtain the solution of a problem. Okay? All right. Let's talk a little bit about spaces. So far, we talked about the energy space only, right? Energy space is a set of functions for which we have finite energy, right? We don't want something, for instance, that we are integrating a function in the domain and then the function goes to infinity. That makes no sense. If you get an infinite result, then what does it really mean to have infinite strain energy? You're not going to be able to work with that, right? Things break apart in mechanics when you go to infinite. So we're dealing with functions in the so-called energy space. Mathematicians look at this from a different perspective. They say, well, I want to work with the so-called Sobolev functional spaces. So a Sobolev functional space, right, you can write it simply like this. Mathematically, it's a set of functions V that are in the so-called Lebesgue space L2, right, which is simply saying, by definition, that the function integrated over the domain squared, right, has to have a finite value. So in a way, look at the similarity between our so-called energy space and this Lebesgue space, that we are enforcing that we're dealing with functions that we can actually integrate, right? But in addition to that, we are required that the derivative is square integrable. So not only the function itself, right, has to become part of L2, but also the derivative has to be part of L2, right? And so it makes sense because remember that in the bilinear form, we don't have the functions themselves, we have the derivatives. So the derivatives have to be square integrable. So as long as the derivatives and the functions give you a finite result, we say that that is basically part of the so-called Sobolev space H1. Now, of course, you can extend this to high orders. You can have H2, H3, H4. So for instance, H2 would require the function to be part of L2, the derivative to be a function of L2, and also the second order derivative to be part of L2. That would be H2. And there are some problems for which you require the functions to be in H2, okay? But that's all it is. I'm not going to talk more about Sobolev spaces, but it's just for you to know that if you ever read a book or a paper and they talk about Sobolev spaces, this is exactly what it means, right? That you are dealing with functions that have certain regularity, right? That you can actually integrate them and get a finite result, and then when you derive them, you can also integrate those functions. That's all there is to it, okay? All right. There is a little remark that we have to address, which is what happens when we're applying non-homogeneous Dirichlet boundary conditions. So if you recall, a Dirichlet boundary condition was a prescribed quantity on the essential or displacement field for the case of the bar, right? And somehow, if eventually when we solve the discrete problem, you need to prescribe the value of the displacement anywhere in the bar, otherwise, what happens? You were saying something about it. Yeah. You have an infinite number of solutions. So in a way, the fact that you don't prescribe the displacement anywhere, right, can lead to a so-called singular stiffness matrix, for which, well, if you have a singular stiffness matrix, that doesn't mean that you don't have a solution. It means that you have an infinite number of solutions. So in a way, you can solve the problem still, right, because it is possible to solve singular problems, but you solve it up to a constant, right? And for instance, in the case of a simple one-dimensional bar in compression or tension, then if I don't prescribe the displacement anywhere in the bar, right, this bar can simply translate in space and have any position, and that's what it means by an infinite number of positions, right, or solutions. But I can still solve for the strain in the bar. I can still do that, right? And there are ways to do that, right? You can actually solve for singular systems. Who knew that, by the way, that you can solve for singular systems? Okay, not many. Now you know. You can actually solve for singular problems. But again, you solve up to a constant. So if you are interested in the stress of a bar, that's perfect. If you're interested in the displacement, well, the displacement is in a way meaningless, unless, of course, it is related to another displacement in the bar. Again, we go back to the strain or stress. Okay, so how do we deal with with the fact that if I want, at some point, I want to prescribe the displacement to certain value. I want to say on the left of the bar, I want the displacement to be equal to 1 centimeter. Well, this is basically a so-called non-homogeneous or non-zero essential boundary condition, right? And we have to talk a little bit about this because there is a little subtlety that we need to address, right? Because remember, the idea is that we are going to pick these functions, the function u and the function w, they are from the same space, right? Well, in the case of non-homogeneous boundary conditions, they cannot be from the same space, right? And so what we do is we say, we're going to define a space V naught, right? So that the function is equal to 0 in the part of the domain where you're prescribing the displacement. So you are saying here, V is in the H1 Sobolev space, but also the restriction to that V function is equal to 0 in gamma D. And if you recall gamma D, we denote gamma D, the part of the boundary where we're prescribing the essential boundary condition, right? The Dirichlet boundary condition, that is the D for Dirichlet, right? And so now what we're going to say is, imagine that you have some function u tilde. U tilde is going to satisfy my boundary condition. So this u tilde is going to be equal to 1 at the left boundary. So that function satisfies the essential boundary condition. What we're going to do is we're going to define what is called a linear variety. And the linear variety is simply, I take this space, right, which is really a big set of functions, and I'm going to say, I'm going to translate every function in that space by that other function u tilde. Yeah, so it's essentially a translation of an entire space by some u tilde function that we know satisfy a priori the essential boundary condition, okay? Well, so now that we have that, all we have to do is now we find a solution. So we change the statement of equilibrium, and we're going to say, well, now the variational form is find u in that linear variety, right? So that bu, w is equal to lw, so the bilinear form equal the linear form for all functions w in v naught. And notice that here I have w's in v naught, and then I have u in the linear variety. So I am really taking things from different sets, okay? And why is this important? Well, because now I can write the function that I'm interested, this is the final function, u, as this addition of two functions, v and u tilde. U tilde is the function that I know, right? I know that it's going to be satisfying the displacement equal to 1 on the left. I know that. And then v is the unknown part of the solution. So you see, I'm basically applying a trick where I'm saying I'm going to write my solution as the sum of two components, one that I know and one that I do not know, right? So this one that I know is straightforward, I know it, and I'm going to take v from the same space as the weight functions. And now my alternative equilibrium statement is going to be, if I plug this guy here, I plug it here, right? And I apply the distributed property of the bilinear form, I simply get back this expression where on the left hand side, the bilinear form, I have b of v comma w, again, the unknown part of the solution. And on the right hand side, now I have this term. So after I apply the distributed property, the part that I know goes to the other side of the equation, right? And in a way, the u tilde, which satisfies the boundary condition right here, is now showing up on the right-hand side. And we have to address this because now you understand that when we know that the displacement is going to be prescribed on the left of the bar, that information is very important because somehow it's going to change what eventually will become my force vector in the discrete formulation. Remember that everything that you have on the left-hand side of this equation is going to lead to the so-called stiffness matrix, right, times the displacement unknown vector. And everything that I have on the right-hand side is going to be the force vector, right? So Now that we know that the displacement has to be equal to 1 on the left-hand side, that information is important because it's actually changing my right-hand side of the equation. Okay? So, in a way, now we have changed the problem, and now we are dealing with the same space, because notice I need to find V in V naught, right? Such that this expression holds for every weight function in V naught. So now I'm dealing with the same functions. I'm taking V and W from V naught. And this is also something very important, because the fact that I'm using functions from the same functional space means that this guy here, the bilinear form, is going to have nice properties. There's the symmetry property, right? Which eventually is going to lead to a symmetric stiffness matrix. And having a symmetric stiffness matrix is good because it is easier to solve, you require less operations, it requires less storage, right? It has nice properties, right? It does not mean that you cannot choose different spaces, right? There are problems, and we talk a little bit about this. What we are discussing here is the so-called Bubnov-Galerkin eventually, when we're taking functions from the same space. You can also have the so-called Petrov-Galerkin, where you're taking the function or the trial solution U and the test function from different spaces, and those formulations have different properties, right? But now we know that we transform the problem, so it's a little trick that we apply by defining this so-called linear variety. We transform the problem so that now we are interested in finding the unknown part of the solution in this space V naught. That's all there is to it, nothing much more. And there is another thing that you probably realized already. The fact that I'm enforcing that this function is equal to 0 along the boundary with Dirichlet boundary condition, right? What is essentially going to do? If I look at my variational form and I look at this term, if I'm basically saying that this guy here is going to be equal to 0 where we apply the Dirichlet boundary condition, what is happening?
The term vanishes.
The term, which term?
The boundary condition term.
At the Dirichlet boundary condition, one of these forces is going to be the so-called the reaction, right? So now we're saying, okay, since I'm going to make sure that W is equal to 0 at the boundary with Dirichlet boundary condition, I'm just basically going to get rid of the reaction term. It's not going to pop up in the formulation. Yeah, it's going to make the formulation simpler. Okay, let's look at an example. Now that we have 1 minute, consider a prescribed displacement U at 0 equal U naught at the left end, and a mixed boundary condition. Again, you can apply any boundary condition on the right. I chose for this example a mixed or Robin boundary condition. Remember that the Robin boundary condition was a combination. You could see it as a combination between a Newman or a Dirichlet boundary condition, depending on the value of this guy H. So if H, the spring constant H, is very, very high, we are essentially enforcing a Dirichlet boundary condition, right? And if it is very, very low, yeah, essentially a Newman boundary condition. So what do we do? Well, now we are going to write the expression, the weak form. And for a Robin boundary condition, there is essentially this term that pops up. And then recall that we have the reaction on the left. So this is exactly the same equation we had before. It's just that now we're dealing with this Robin boundary condition, right? So you have this term that has to be accounted for. When you integrate by parts, you have the expression for the boundary terms. So you just basically replace that by this, and that is what you have here, right? And so R is a reaction force, but again, since we're setting our functions so that they vanish at that part of the boundary, this term is essentially going to be 0, right? And so if you notice, the Robin boundary condition has two parts. One that you know, this is the one that you want to prescribe, right? To the left, to Earth, this is what I want to be 1 centimeter. There is one that is unknown, and essentially the one that is unknown becomes part of the bilinear form. The ones that is known, again, everything that you know goes to the right-hand side, and it changes our linear form. And that is why in the end, we write the statement of equilibrium like this. Same thing that we just did in the previous slide, where we express our function u, right, as the sum of two functions, one v, that is the unknown, and u tilde, that satisfy the boundary condition on that left end. And then we have our statement of equilibrium, right? Find v, which is the unknown part, in v naught, such that my bilinear form is equal to the linear form minus the effect of the applied prescribed non-zero essential boundary condition. And then, of course, you write the expressions for both the bilinear form and the linear form. So notice that in the bilinear form, the new term is simply this one that arises, again, from the Robin boundary condition. And then on the right-hand side, the term also arising from the Robin boundary condition. This term is the part that you don't know. This is the part that you know. So very simple. This is the statement of equilibrium for this example. Okay. Remember that all of this is very, very well explained in the book. So if you read and you have doubts, go through the material and look at in Nota Bene. If you don't understand something, you can place comments there. We can discuss it there. But what I did now in these few minutes is to go really, really quick through some of the material in the book. But of course, you have it in more detail there. Okay. Any questions up to this point? Yeah.
Can you give an example of what utility might actually look like?
Sorry?
Can you give an example of what the utility might actually look like?
Yeah, say for instance, say you have polynomial function, to make it simple, and then it's a quadratic function, and then it has certain value at the left end. That is going to become your u tilde. Again, u tilde can be anything as long as it satisfies the value that you want at that boundary. It could be any function, right? Normally, when we're dealing with finite elements, we are dealing always with lower order finite interpolants, right? So polynomials of order 1 or order 2 at the most with HFEM. And when we're dealing with PFEM, you're going to see also later in this course that we can go up to an arbitrary order, essentially. Yeah? Yeah? Yeah?
Take the problem statement given u is v plus u with the filter.
Yeah? So
Do you, I assume, plug that into the previous equation, the v form?
yeah,
What is v denominated then?
this v,
In your end equation?
yeah, so if you recall, we had in the bilinear, so the weak form of equilibrium was the bilinear form equal to linear form, right? So the moment I write my function u like this, that is comprised of a part of the function that I know, which is u tilde, and one that I don't know, which is v, I plug that into the bilinear form, and then I apply the distributive property. So now you have two bilinear terms, right? The part that you know goes to the other side. So again, everything here on the left is what I don't know. It has this v component, and everything on the right is what I know. So is that what you're asking?
I got what you did. Thank you.
Okay. All right. Excellent. We take a little break, and then we continue to the Galerkin projection.